Hey everybody, we're back with the second part of integration using partial fractions. And here we're going to look at case 3. This is when a proper rational function has distinct irreducible quadratic factors in the denominator. Now, when we talk about irreducible, it just means that the quadratic factor, cannot be factored using real numbers. If that happens, then that means the discriminant is going to be less than 0. Remember, the discriminant is the b squared minus 4ac part of the quadratic formula. And if that's less than 0, that ends up meaning you have a negative under the radical, which therefore indicates you have no real roots. So for this first one here, we're going to factor the denominator. You also want to check if the numerator factors, because once in a while you're going to be able to cancel factors. Now this numerator is not going to factor. So when you have quadratic factors, the numerator of your partial fraction decomposition has to be 1 degree less. So let me show you what I'm talking about. So the x right here is a linear factor. So that's going to be a over x. But the x squared plus 4 factor is a quadratic factor. The numerator is going to have to be bx plus c. Okay, because the numerator could have been a linear or a constant, so we have to account for both cases. So we're going to do the same process from here on out as we did in case 1 and case 2. We're going to multiply it by the common denominator. So you'd end up with 2x squared minus x plus 4 equals a times x squared plus 4 plus bx plus c times x. Now, if I pick the strategic value of x equals 0, then you would just have 4 equals 4a, because the bx plus c term is going to be multiplying by 0, so that's going to make it 0. So this means a equals 1. Now, at this point, there are no other strategic values that are going to cancel anything, and it could get a little bit confusing trying to pick other values. Another technique that you can use here is if you have the value of a, we can plug that in. So that means this would be x squared plus 4. I'm working with this one. And then if I FOIL or distribute, I would have bx squared plus cx. That's got to be equal to 2x squared minus x plus 4. Now what I can do is something called equate coefficients. So if I gather my x squared terms and factor out the x squared, that's going to be 1 plus b. The x squared term has to have a coefficient of 2, so that further tells me that 1 plus b has to equal 2. So b equals 1. Isn't that pretty cool? And then the x term, I can equate the terms with the coefficient of x. So there is only one term that has a x, that's the cx. So I also know that cx has to equal negative 1x. So c has to equal negative 1. Our integral would be the integral of 1 over x plus 1x. So the first one is going to be natural log absolute value of x plus, now the 1x minus 1 over x squared plus 4, we can't do it the way it's written. It's not a log rule. It's not u prime over u. But since there's subtraction in the numerator over the common denominator of x squared plus 4, we can split it up as the integral of x over x squared plus 4 dx minus 1 over minus the integral of 1 over x squared plus 4 dx. Now we have natural log absolute value of x. The next one is going to be 1/2 natural log of x squared plus 4. You don't need the absolute values because x squared plus 4 is never 0 or negative. And you would have to have a 1/2 there because the u being x squared plus 4, the u prime would be 2x. Since there's not a 2 there, you need 1/2 to cancel it. And this last one should be recognizable as arctan. So it's 1 over a, which in this case, the a is 2 because the 4 is playing the role of a squared. So it's 1/2 tangent inverse of x over a, so x over 2 plus c. And there we have it. All right, so let's move on to another example with this one, just to kind of get you a feel for it a little bit more. Notice that the denominator is a cubic, but it's a difference of cubes. And so we could factor the denominator as x minus 1 times x squared plus x plus 1. If you remember your formula for difference of cubes. Now, here we have a linear factor and a quadratic factor. So we'll have to have a over x minus 1 plus bx plus c over x squared plus x plus 1. Also, the x squared plus x plus 1 is irreducible because its discriminant would be less than 0. So clearing the fractions, you would have 3x equals a times x squared plus x plus 1 plus bx plus c times x minus 1. Picking the strategic value of x equals 1, you would have 3 equals a times 3, and the last term would go away. So you would have a equals 1. And then from there, we can equate coefficients. So 3x equals, if a is 1, then this would just be x squared plus x plus 1 plus, now foiling the bx plus c times x minus 1. If I did the first, you would have bx squared, the outer minus bx, the inner plus cx, and the last would give you minus c. So equating coefficients, I know that if I put the x squared terms together and factor out the x squared, I'd have 1 plus b. If I put the x terms together and factor out the x, I'd have x times 1 minus b plus c. And then the constant terms, I can put those together plus 1 minus c. Now, there are no x squared terms, so I know the 1 plus b has to equal 0, so b equals negative 1. So this x term here, the coefficient is 3, so I know 3 has to equal the 1 minus b, which we just found to be negative 1, plus c. So 3 equals 2 plus c, so c equals 1. And also, just to check, if the constants are 1 and minus c, and c is 1, 1 minus 1 is 0, and notice the 3x term has no constant with it. Okay, so now we have a equals 1, b equals negative 1, and c equals 1. So we can now set up our integral. 1 over x minus 1 plus negative x plus 1 over x squared plus x plus 1 dx. First integral is going to be natural log absolute value of x minus 1. Now this second one, this is where things get a little bit complicated because we can separate the minus x and the plus 1 into two separate fractions, but still that's not going to help us because we're not going to necessarily get a tangent inverse or a natural log form. What we have to do is actually complete the square for the denominator. So that if I just look at the denominator, you have x squared plus x. The coefficient of x is 1. If you take half of that and square it, you would have 1/4. So you add 1/4, then subtract 1/4, and then plus the 1. This right here is our perfect square. So that's going to be x plus 1/2 squared. And then the minus 1/4 plus 1 is going to give us plus 3/4. So this is going to be the integral of negative x plus 1 over x plus 1/2 squared plus 3/4 dx. Now I'm going to have to use a little bit of u substitution here. I'm going to let u equal x plus 1/2. Du is dx, and x is going to equal u minus 1/2. So I'm just going to isolate that integral. So I would have the numerator is going to be the opposite of x, so that's going to be negative u plus 1/2 plus 1 over u squared plus 3/4. Okay, the 1/2 and the 1 are going to combine to give us 3/2. So I'm going to put this, running out of room here, I'm going to put it over here. So I would have negative u plus 3/2 over u squared plus 3/4. So I can think of this as negative u over u squared plus 3/4 plus 3/2 over u squared plus 3/4. Now, if I integrate these, the first one is going to be the log rule. So that's going to be negative 1/2 natural log of u squared plus 3/4 plus 3/2. The second one is the tangent inverse, where the a squared is 3/4, so square root that, you get square root of 3 over 4. So, or square root of 3 over 2. So you'd have 2 over root 3, tangent inverse of 2u over root 3. Now back substituting what the u is x plus 1/2. So this is going to be negative 1/2 natural log. Now if I do u squared, remember the x plus 1 was the factor for the perfect square, plus the 3/4 gets me back to the x squared plus x plus 1, plus these fractions right here are just going to simplify to root 3, tangent inverse of 2 times x plus 1/2, which is just going to be 2x plus 1 over root 3 plus c. But don't forget, all the way back here, we had this first term here, natural log of x minus 1/2. So we're squeeze that in there, natural log of x minus 1. And that, ladies and gentlemen, is our answer. A little bit of convoluted work there, but hope that was helpful to you. Okay, the next thing we want to look at is a situation where you have a proper rational function that has repeated irreducible quadratic factors. So this is how we're going to do this one. It's the same as with linear factors, except you're repeating the quadratic form of them. So for this one, you would have 8x cubed plus 13x over x squared plus 2 squared is going to be ax plus b over one of the factors of x squared plus 2 plus cx plus d over x squared plus 2 squared. If we had an extra x in the denominator here, we would have to have started off with a over x, and then you would have bx plus c over x squared plus 2, and so forth and so on. All right, clearing the fractions, you would have 8x cubed plus 13x equals ax plus b times x squared plus 2 plus cx plus d. Now, at this step, what we can do is just start off by equating coefficients. So we're going to FOIL the ax plus b with the x squared plus 2. So you'd have ax cubed plus 2ax plus bx squared plus 2b plus cx plus d. If I equate coefficients, I would have ax cubed plus bx squared, takes care of those, plus x times 2a plus c plus 2b plus d. Those are going to be the constants. So I know that a has got to be equal to 8. I know b is going to be 0 because there is no x squared term. The 2a plus c has to equal the coefficient of x, which is 13. So a is 8, so that's going to be 16 plus c equals 13. So c equals 3. This should have been a D right there. So the 2b plus d has to equal 0. If b is already 0, then d equals 0 as well. So setting this up, I would have the integral of 8x over x squared plus 2 minus 3x over x squared plus 2 quantity squared. This should have been negative 3 dx. Now the 8x over x squared plus 2, that's just the natural log form. You would end up with 4 natural log of x squared plus 2. The absolute values aren't necessary in that case. The 3x over x squared plus 2 quantity squared, we could use u substitution with u equal x squared plus 2, du equals 2x dx. I have a 3 there, so I'd multiply both sides by 3 halves to get 3x dx. And then the antiderivative is going to be plus 3 over 2 times x squared plus 2 plus c. So that one was actually pretty straightforward in terms of solving it. The last one I want to do is another example here, and it's going to get a little bit complicated. So here we have a repeated quadratic factor that is irreducible. So you would have x cubed plus 1 over x squared plus 4 squared. That's going to be ax plus b over x squared plus 2 plus cx plus d over x squared plus 4 quantity squared. Clearing the fractions, you would have x cubed plus 1 equals ax plus b times x squared plus 4 plus cx plus d. Again, in this case, we're going to FOIL everything out and equate coefficients. So you'd have ax cubed plus bx squared plus x times 4a plus c plus 4b plus d. Now a is going to be equal to 1. There is no x squared term, so b equals 0. There is no x term, so 4a plus c equals 0. If a is 1, then c has to equal negative 4. And then 4b plus d has to equal 1. If b is 0, then d is going to be 1. So our integral would be x over x squared plus 4 minus 4x plus 1 over x squared plus 4 quantity squared dx. Now we're going to add these because just the 4 is negative in the numerator there. This first integral is pretty straightforward. That's just going to be 1/2 natural log of x squared plus 4. The second one, we're going to actually go ahead and split that apart and write this as negative 4 integral x over x squared plus 4 quantity squared dx plus the integral of 1 over x squared plus 4 quantity squared dx. This integral right here is similar to one we've done before where we do u substitution with u equals x squared plus 4, du equals 2x dx, but you have a 4 there, so 2 du equals 4x dx. And then this is going to be 2 times the integral of 1 over u squared. Okay, so this is going to end up being negative 2 over x squared plus 4, but since it's being subtracted, this is going to make it plus. So plus 2 over x squared plus 4. Now this last one, we're going to have to do something called trigonometric substitution, and here's how we do this. Notice you have x squared plus 4. It's not inverse tangent because the whole quantity is squared, and you can't do u prime over u squared or anything like that because the numerator is just 1. If we look at a right triangle, because the x squared plus 4 is like part of the Pythagorean theorem, that reminds us of the square root of x squared plus 4, which is the hypotenuse. That would make this side x and this side 2. If our reference angle here is theta, then tangent theta equals x over 2, and then 2 tangent theta equals x. If I differentiate, I'd have 2 secant squared theta d theta equals dx. That takes care of substituting the dx, but I need to substitute the square root x squared plus 4. Now, the square root x squared plus 4 is in the hypotenuse, so it's got to be one of the trig functions that involve the hypotenuse. I'm not going to want to involve the adjacent side because that's going to introduce an extra x. So if I do secant theta, that's hypotenuse over adjacent, or the reciprocal of cosine. Then that would be 2 secant theta equals square root x squared plus 4. Guess what we're going to do? We're going to square both sides and get 4 secant squared theta equals x squared plus 4. And this is how the trigonometric substitution works. Then I just substitute everything I have. The dx is 2 secant squared theta d theta. And the x squared plus 4 is 4 secant squared theta. But that quantity is being squared, so this actually is going to be 16 secant to the 4th theta. Simplifying that, I would have a 1/8 factored out, and then 1 over secant squared theta d theta. Now, secant is the reciprocal of cosine, so this is 1/8 cosine squared theta d theta. The problem is we don't know the antiderivative of cosine squared, but there is the identity for cosine squared where we could write it as 1 plus cosine 2 theta over 2 d theta. So I'm going to factor out that 1/2 and make the 1/8 a 1/16. And then the antiderivative of 1 is theta. And then the antiderivative of cosine 2 theta would be 1/2 sine 2 theta. Then from there, the 1/16 times theta plus 1/2 sine 2 theta is equal to sine theta cosine theta. Because you can't have sine of 2 theta because our triangle's reference angle is theta, not twice theta. We can now back substitute in terms of x because these are all in terms of theta. If we have tangent theta equals x over 2, then that means that theta is going to be the tangent inverse of x over 2. So 1/16 of tangent inverse of x over 2 plus sine theta would be opposite over hypotenuse, so x over square root x squared plus 4 times cosine theta is adjacent over hypotenuse, so 2 over the square root, and all of that is multiplied by 1/16. So if we simplify and distribute at 1/16 tangent inverse x over 2 plus x over 8 times x squared plus 4. The x squared plus 4 radicals multiply together and you just get what's inside. The 2 and the x multiply, giving you 2x, but that cancels the 2 with the 1/16, giving you 1/8 plus c. And then we have to bring everything else down that we had previously. So there you go. I told you guys this one was going to be a little bit complicated, but I hope that was helpful to you. All right, guys, that's it for this section. We're going to wrap it up there. Take care.